Hello everyone, this is Andrew again, and now we're going to discuss Instrumentation and Controls Part 2 Basic. Okay, let's start. On this lecture, we're going to discuss what is a digital signal, analog to digital conversion, digital signal, analog signal, and PLC data processing. Okay, as you can see, this is the exercise from our previous lecture. And it will take time and effort to read, interpret, and record data from the instrument. If we will recall our last discussion, we need to read the value of the voltmeter here, and we need to use the table so that we can read the temperature. But as you can see here, it will take time and effort to read, interpret, and record it. Now let's discuss what is a digital signal. Digital signal, it is the signal used to represent a data in a sequence of multiple discrete values or binary numbers. Take note, computer can only understand binary codes. And this is an example of an 8-bit binary code. Computer system is very useful in our daily life. It can quickly process the given input and give you the result immediately. One example of this system is a calculator. When you input a data, you can get the answer immediately. And this one, if we can read the data from the instrument and put it on the computer, the recording, analyzing, viewing of data will become faster. To view, record, and to interpret the process variable from the instrument, the signal should be converted to digital signal. The computer cannot understand number 4, but it can understand 0100, or it is the binary equivalent of number 4. Measuring instrument produce analog signal to send the value of the measured process variable, but computer can only understand a digital signal. The signal from the instrument must be converted to a digital signal. And we have a question here. Is analog to digital conversion accurate? The answer is no. Why? As you can see here, this is an analog signal, and this one is the digital signal. And sometimes the digital signal is not equivalent to the analog signal. There is an inaccuracy. And because of that, the analog to digital conversion is not accurate. But we need to convert it to make the work faster. And now the only solution that we can do is to increase the accuracy of the conversion. We need to increase the resolution of the analog to digital converter to increase the accuracy. As you can see now, if we increase the resolution, the data becomes more accurate. Okay, let's have this exercise. Find the step size of analog signal with URV of 5 volts and LRV of 1 volt if the converter has a 3-bit data. And to find the step size, we have this formula: span over 2 raised to number of bits minus 1. First, we need to solve for the span. Then, we need to solve for the resolution. After that, we can get the step size 0.5714 volts per resolution. And the percent error will be 1 over 2 raised to number of bits minus 1 times 100%. And as you can see here, we have 14% error. And as you can see here, we have 1 volt. We have a digital signal of 0. And we have the decimal value here, 0. Then 1.5714 volts. We have an equivalent digital signal of 001 and so on. The digital signal is the signal that can be understood by the computer, while the decimal value here is for human interpretation. Okay, let's have this one. Find the step value of analog signal with URV of 5 volts and LRV of 1 volt if the converter has a 4-bit data. Okay, please pause this video and try to solve it by yourself. Okay, let's continue. First thing is we need to find the span. Then find the solution. Okay, we have this result. We have a percent error of 6.667%. And as you can see here, if we have 1 volt, we have a digital signal of 000. And if we have 1.266 volts, it is 0001. And the inaccuracy here is when the value is between 1 and 1.2 volts. Next, this is the data from our previous lecture. We have a 10 degrees Celsius here. The analog signal is 1 volt, digital signal of 000, and here 23.33. We have equivalent analog signal of 1.2667, and the digital signal is 0001. And as you can see here, if we have a value of 15 degrees Celsius, there's no equivalent digital signal, and that makes it inaccurate. Find the step size of analog signal with the URV of 5 volts and LRV of 1 volt if the converter has an 8-bit data. Okay, please pause this video and try to solve it by yourself. Okay, let's continue. Okay, before we continue, don't forget to subscribe to our YouTube channel. Please click the notification bell to notify you for new video. Don't forget to like and share our videos. Please like our Facebook page and click see first to notify you for new posts. If you like this video, please put a comment nice below. First, we need to find the span, then the resolution, then this will be the step size, 0.0156 volts per resolution. We have 0.3921% error. Then here, because we have 8-bit resolution, if we have an instrument reading of 10 degrees Celsius, we have an analog signal of 1 volt, and we will have this digital signal. Then the next value will be 10.78. And as you can see here, the accuracy increases. Unlike the last one, there is no equivalent digital signal for the values between 10 degrees Celsius and 23 degrees Celsius. But as you can see now, we can read the value between them. Okay, let's discuss about digital signal, analog signal, and PLC data processing. Let's say we have a process variable here. Then after the measuring instrument exposed to the process variable, it will release a substandard signal. And here, the transmitter will convert the substandard signal into a standard signal in analog. Then after that, it converts the analog signal to digital signal. Now the digital signal can be manipulated and used in programming. Then the data can now be transmitted to HMI using serial communication or Ethernet communication. And here, the user can read the process variable even if the instrument is field mounted. Let's say that we're measuring a boiler and the temperature is approximately 120 degrees Celsius, which is hazardous. And because of this system, the user can read the temperature even if he is not on the field. Create a PLC program to monitor the level of the tank. The alarm indicator will turn on if the corresponding water level is reached. We have a level transmitter here. We have a PLC data memory of D1000. We have the instrument output of 1 to 5 volts. We have the upper range value of 300 mm, lower range value of 0 mm, resolution of 1024, and these are the alarms. First thing that we need to do is to get the corresponding resolution. We have the lower range value of 0 mm and upper range value of 300 mm. Then we have 100 mm here. And for the upper resolution, we have 1023. And for the lower resolution, we have 0. And now, using interpolation, we can get this resolution 341. It means at 100 mm, the reading at the PLC is 341. Next, let's solve for 50 mm. Okay, then we need to round it up for safety purposes. Next, we have 250. We need to round it down for safety purposes also. Then last, we have 280. Then we need to round it down for safety purposes also. After getting the corresponding resolution, we can create the PLC program here. If the PLC reading is equivalent to 171 or equivalent to 50 mm, the lower alarm low will turn on. Then, if the value is 341 or equivalent to 100 mm, the lower alarm low will turn on. If the value is 852 or equivalent to 250 mm, the lower alarm high will turn on. And if the value is 954 or equivalent to 280 mm, the level alarm high will turn on. And that's all for today. Thank you for watching this video. Please subscribe to my YouTube channel. Click the notification bell to notify you for new video. Please like and share my YouTube videos and like my Facebook page.
Please click see first on our Facebook page to notify you for new posts. If you like this video, please comment nice. Please comment negative and colon and put your negative comments about this video. Please type suggestion semicolon and put the suggestion about this video. And if you think that this video needs some improvement, just type improvement semicolon and put the things that you want to improve about this video. I will use all of your comment, negative comment, suggestion, and improvement so that I can improve all my future videos. Thank you for all the feedbacks. And thank you again. See you next time.